Hello guys, we're gonna start with simple harmonic motion now. This is the first video and we're gonna introduce what is simple harmonic motion in this video, and we'll discuss what the characteristic of simple harmonic motion are. Right, this is what a simple harmonic motion does. Suppose this is a particle and it is x distance away from a fixed point. Now, a simple harmonic motion, what it does is that this particle will move away from a fixed point and comes to 0, then again turn around and move back. So when it passes this point again, it decelerates until it becomes 0, the velocity is 0, then turn around and come back. So this is called simple harmonic motion, right? So it actually an oscillation. So what are the characteristics of simple harmonic motion is that, now look at this diagram. We take this point to be the fixed point. You know, when we describe the displacement of a particle, we always describe the displacement with respect to a fixed point. So this is a big fixed point, and if this is the x displacement, you know the acceleration can be represented by x double dot, right? Can be represented by x double dot. Here you can see, okay, x double dot. Now in this case the acceleration is away from 0, that have I mentioned here, right? So what are the characteristics of this motion? See, for a particle to be in simple harmonic motion, the acceleration should always be directed towards a fixed point. So like in this case, now when it is moving away from acceleration, away from O, the acceleration is towards O, right? So therefore it is moving with deceleration in this direction, right? So that's why it comes to rest, then move, turn around and come back. So when it is coming back towards O, then it is accelerating towards O. So when it just passes O, what happens? The direction of the acceleration changes, therefore it starts to move with deceleration until it comes to rest and turn around, come back. So that's how it moves. So the acceleration is always directed towards a fixed point, and this fixed point is called the center of simple harmonic motion, right? So in this case, this would be the center. Right, this is the center. Now, this is a qualitative idea of the acceleration. So, what is the quantitative idea? Quantitative idea means how much. What is the acceleration quantitatively? So, the acceleration is proportional to the displacement with respect to the center. So, they say that the acceleration is proportional to the displacement. That means, so acceleration can be written as x double dot. This is proportional to the displacement x, proportional to the displacement x. Okay, so now this proportionality constant can be taken out by introducing a constant. So x double dot minus omega squared x, x double dot minus omega squared x. Now here this omega is angular velocity, as you know. Omega is the angular velocity. Right, so this is called the characteristic equation of simple harmonic motion. This is called the characteristic equation of simple harmonic motion. CHA, equation of simple harmonic motion. Now, if you want to check whether a particle is moving in a simple harmonic motion, then you can have to attest to this. Attest if the motion is satisfying this equation right here. So, if the motion satisfies this equation, then we can say that the particle is moving in simple harmonic motion. Right. So, we'll look at some examples now to check whether the motion is simple harmonic or not. Suppose, for example A. So let me give the displacement as a function of time. So x, say that this is a sine omega t. So we want to check whether this motion, the motion described by this equation, follows simple harmonic. So what we do here is that we derive this equation with respect to time. So dx by dt a cosine omega t times omega, the first derivative. Second derivative, d squared x over dt squared is that now this becomes minus a minus sine omega t. Then you're going to have to multiply this by omega again. So this becomes omega squared. So what we get here is that minus omega squared a sine omega t t squared. Now this is, what is this one? This is actually x. So we can replace it, minus omega squared x, and this is called the x double dot, right? So you can see that the motion described by this equation follows simple harmonic motion. Now let's look at another example. Another example would be, you can do this one by yourself. Say B. This is, let me change this to cosine omega t plus alpha, right? So you can try this example by yourself. Okay. Then example C, suppose, let me take another variable y, a exponential omega t. So let's see whether this motion, the motion described by this equation, follows simple harmonic motion. So just take the first derivative, dy by dt is equal to a. You get the exponential back, but you have to multiply this by omega. Okay. If you take the second derivative, d squared y over dt squared, you get same thing, but again you have to multiply by omega. Now what you get here is that omega squared a e omega t, omega squared a e omega t, and d squared y over dt squared is actually y double dot is equal to omega squared. This part is y. Now notice here that this is quite similar to the characteristic equation, but something is missing here. What is missing? Then it is missing this negative sign. So this is not simple harmonic motion, not SHM. If it is simple harmonic motion, it must satisfy this equation with a negative sign there. Okay, thank you for listening.